Welcome everyone. I'm excited to kick off today's presentation. Today we'll be exploring the magnetic effect of current, part II. This is the first slide, so I just want to give you a quick overview. We'll be diving into the basics of how electric currents generate magnetic fields, understanding some key concepts, and exploring interesting applications. So let's get started and see what this fascinating topic has in store for us. Let's now look at how we can convert a galvanometer into an ammeter and a voltmeter, which is an essential aspect of measuring current and voltage in circuits. We'll also touch upon some fundamental concepts like the definition of an ampere, which is the SI unit of current, and the moving coil galvanometer, which forms the basis of these instruments. Next, we'll explore the forces between two parallel, infinitely long current-carrying conductors, a key principle behind magnetic fields generated by currents. Understanding this helps us see how magnetic forces act at a distance. We'll then examine the differences between ammeters and voltmeters, what makes each device unique, and how their construction and functioning vary to suit their specific measurement purposes. Moving forward, we'll discuss the torque experienced by a rectangular current loop in a uniform magnetic field. This is crucial for understanding how electrical energy is converted into mechanical motion in devices like galvanometers. Additionally, we'll cover the force on a moving charge in uniform electric and magnetic fields, which is fundamental to many electromagnetic applications. We'll also look at the representation of the magnetic field due to parallel currents, helping visualize how currents create magnetic effects in space. Finally, we'll revisit the Lorentz magnetic force, a key concept that explains how magnetic fields exert forces on moving charges, tying all these ideas together. By understanding these core topics, we'll see how they interconnect to form the foundation of electrical and magnetic measurement tools used in science and engineering. Let's look at the maximum magnetic force, which is given by the equation Fm max equals Q times V times B now. If the angle theta between the velocity of the charge and the magnetic field is 90 degrees, meaning the charge moves perpendicular to the magnetic field, the force reaches its maximum value. This is because the sine of 90 degrees is 1, so the force is at its strongest. On the other hand, if the charge moves parallel or anti-parallel to the magnetic field, so when theta is 0 or 180 degrees, the force becomes 0. This is because the sine of these angles is 0, resulting in no magnetic force acting on the charge. Additionally, if the charge is at rest, meaning its velocity v is 0, then the magnetic force is also 0. So, a stationary charge in a magnetic field doesn't experience any force at all. This highlights an interesting point. A moving charge experiences a force in a magnetic field, but a stationary one doesn't. And this idea extends to currents in conductors. When a current-carrying conductor is placed in a magnetic field, it also experiences a force. In summary, the magnetic force depends on the charge's velocity, the magnetic field, and the angle between them. When the charge moves perpendicular, the force is maximum. When it moves parallel or is stationary, the force is 0. When a charge, which we denote as Q, moves through a region where both electric and magnetic fields are present, the force acting on it is described by the Lorentz force law. This is expressed mathematically as F equals Q times E plus V cross B, or more compactly, F equals Q times the quantity E plus V cross B. What's really important here is understanding that the total force on a charged particle depends on both the electric field, E, and the magnetic field, B, as well as the velocity, v, of the charge. The electric field exerts a force directly, while the magnetic field's influence depends on the particle's motion, specifically the cross product of v and b. This concept is fundamental because it explains how particles respond differently depending on whether electric, magnetic, or both fields are acting upon them, and it's a key part of understanding electromagnetic interactions in various applications. So, when we talk about the force on a charge in these combined fields, keep in mind that the magnetic part only acts when the charge is moving, making the velocity a crucial factor in how the overall force behaves. This idea ties back to our overall theme of how electromagnetic fields influence charges and currents in different physical systems. Let's focus on this useful tip. Remember the phrase EMF. This helps us keep track of the 3 key directions in Fleming's left-hand rule. The idea is to visualize the electric current, the magnetic field, and the force acting on a current-carrying conductor, all in the context of the fingers of your left hand moving in a specific way. Now, if you stretch out your left hand so that the central finger, the forefinger, and the thumb are all perpendicular to each other, that is, at right angles, you can use this as a guide. If the central finger points in the direction of the current, the forefinger then points in the direction of the magnetic field. And, importantly, the thumb will point in the direction of the force, or the motion, on the conductor. This method is particularly helpful because it visually connects the 3 directions and makes it easier to understand how the magnetic force acts on a current-carrying wire in a magnetic field. It's a powerful way to remember the relationship and predict the direction of forces in electromagnetic systems. Let's take a closer look at the force experienced by each electron in the conductor. As shown here, the force is given by the equation F equals negative E times the cross product of the drift velocity, and the magnetic field, B. This tells us that the force on each electron depends on its charge, the magnetic field, and its velocity. When electrons move through a magnetic field, they experience a force perpendicular to both their direction of motion and the magnetic field itself. This is a key concept because it explains how magnetic forces influence charge carriers in conductors. Understanding this force is essential for grasping phenomena like the Hall effect and how magnetic fields can manipulate current flow. So, recognizing how each electron feels this force helps us connect the microscopic behavior to the macroscopic electrical effects we observe. Let's consider a small element of the conductor, denoted as dl. If we know the number density of electrons, represented by n, and the cross-sectional area of the conductor, A, then we can determine the number of electrons within this tiny element. It turns out that this number is given by multiplying n, A, and dl. This concept is crucial because when a current flows through a conductor, it's essentially a movement of these electrons. Understanding how many electrons are in a small segment helps us analyze the forces acting on the conductor, especially in the presence of a magnetic field. By connecting these ideas, we see how microscopic properties like electron density influence macroscopic phenomena, such as the force experienced by a current-carrying conductor in a magnetic field. This is a key piece of the puzzle in understanding electromagnetic forces in conductors. Now, let's look at the force per unit length between 2 parallel current-carrying conductors. The formula is quite elegant. It's μ0 times the product of the currents I1 and I2, divided by 2 pi r, where r is the distance between the conductors. Essentially, this tells us that the magnetic force depends directly on the currents and inversely on the distance between the wires. When the currents flow in the same direction, these conductors attract each other, and if they flow in opposite directions, they repel. This relationship is fundamental in understanding how magnetic fields influence conductors and is crucial for designing electrical systems and devices. So, in the broader context, this formula helps us quantify the forces at play and predict how conductors will behave under different current conditions. Now, let's look at the behavior of conductors when they are placed in a magnetic field. When 2 conductors are carrying current, they experience a force that pulls them towards each other. This attraction occurs because of the magnetic forces generated by their currents. To understand the direction of this force, we can use Fleming's left-hand rule. Remember, this rule helps us determine the direction of force on a current-carrying conductor in a magnetic field. In essence, if we align our fingers properly, your first finger points in the direction of the magnetic field, your second finger points in the direction of the current, and your thumb then points in the direction of the force. This visual guide makes it easier to predict how conductors will behave. This concept is fundamental because it explains how magnetic forces influence conductors. which is crucial in the design of electric motors and many other electromagnetic devices. So, the key takeaway here is that conductors with current in a magnetic field will experience a force, and Fleming's left-hand rule is a simple way to determine the direction of that force. Let's talk about 1 ampere and what it really means. Imagine 2 parallel conductors, each infinitely long and placed 1 meter apart in a vacuum. Now, if each of these conductors carries a current of 1 ampere, they will exert a force on each other. Specifically, each conductor experiences a force of 2 times 10 to the minus 7 newtons per meter of its length. This idea helps us understand the definition of an ampere in a practical way. The force per unit length between the conductors is given by this formula. F over L equals mu0 times I1 times I2 divided by 2 pi r here. Mu0 is the magnetic constant, or permeability of free space. I1 and I2 are the currents in the conductors, and r is the distance between them. So, in essence, 1 ampere is the current that produces this specific force when the conductors are 1 meter apart. This definition ties the concept of current directly to the magnetic force it creates, which is fundamental in understanding electromagnetism and the behavior of electric currents. Here, A equals L times B, where L is the length and B is the breadth of the coil. The torque, tau, is given by the formula NIAB cos theta. Now, let's break that down. The torque experienced by the coil depends on several factors. N is the number of turns in the coil, I is the current flowing through it, A is the area, B is the magnetic field strength, and theta is the angle between the plane of the coil and the magnetic field. This formula helps us understand how the coil behaves when placed in a magnetic field. For example, the torque reaches its maximum when cos theta is 1, which is when the plane of the coil is perpendicular to the magnetic field. And it becomes 0 when the coil is aligned parallel to the field, meaning no rotational force acts on it. Understanding this is crucial because it explains how current loops can generate or respond to magnetic forces, which is fundamental in devices like electric motors. So, in summary, the torque depends on the current, the number of turns, the magnetic field, and the orientation of the coil. Now let's look at how torque can be expressed in vector form. On this slide, you see the equation. Vec tau equals N times I times A times B times sin phi. What this tells us is that torque isn't just a scalar value. It can be represented as a vector, which gives us both magnitude and direction. By expressing torque in vector form, we're able to analyze how different factors like current, magnetic field, and the angle between them all contribute to the overall torque experienced by the system. This vector approach is especially useful because it helps us visualize the interaction more clearly and makes it easier to apply in complex scenarios, such as in electric motors or generators. Remember, the core idea here is that torque is not just about how strong the magnetic forces are, but also about their orientation, which is where the sign of the angle, phi, comes into play. So, understanding this vector representation really ties together the concepts we've been discussing about electromagnetic forces and how they produce rotational motion. Let's take a closer look at this key equation. NIAB sin phi equals K alpha. This equation essentially describes the relationship between the magnetic forces and the torsional restoring force in the galvanometer. When the coil is displaced by an angle alpha, the magnetic force produces a torque proportional to these factors, including the magnetic field strength, the current, and the coil's dimensions. At equilibrium, the torque provided by the magnetic forces, which is NIAB sin phi, balances the restoring torque, which is K alpha. This balance point is crucial because it determines the coil's stable position when a current flows through it. Now, focusing on the restoring torque in the coil, it's what brings the coil back to its original position when the current stops. This torque is proportional to the angle alpha, and the constant of proportionality is K, the torsion constant of the spring or suspension. When the coil experiences a current, it feels this magnetic torque, causing it to rotate. The amount it rotates depends on the balance between this magnetic torque and the restoring torque. Understanding this interplay is fundamental to how the moving coil galvanometer works, as it allows us to measure current based on the coil's deflection. So, in essence, the equation encapsulates the core principle. The magnetic torque is directly proportional to the current, and at equilibrium, it's exactly balanced by the restoring torque. This is what makes the galvanometer a precise instrument for measuring small currents. Now, let's look at the concepts of sensitivity in galvanometers, which are crucial for understanding how these instruments respond to electrical signals. First, we have voltage sensitivity, which is defined as the deflection of the galvanometer per unit voltage applied. Essentially, it tells us how much the needle moves when we apply a certain voltage across the device. The higher the voltage sensitivity, the more responsive the galvanometer is to small changes in voltage, making it ideal for measuring tiny voltages. Next, we have current sensitivity, which refers to the deflection per unit current flowing through the galvanometer. This measurement indicates how sensitive the device is to small currents. A galvanometer with high current sensitivity will show a noticeable deflection even with very small currents, which is essential for precise current measurements. Both these sensitivities, voltage and current, are interconnected and vital for the overall performance of a galvanometer. Understanding and optimizing these sensitivities allow us to tailor the galvanometer for specific applications, whether we're measuring minuscule voltages or currents. This ties into our broader theme of instrument sensitivity and accuracy, helping us ensure precise electrical measurements. Now, let's look at how a galvanometer can be converted into other useful instruments. To turn a galvanometer into a voltmeter, we connect it in series with a very high resistance. This high resistance limits the current flowing through the galvanometer when measuring voltage, making it suitable for measuring larger voltage ranges without damaging the device. On the other hand, to convert a galvanometer into an ammeter, we shunt it with a very small resistance. This shunt allows most of the current to bypass the galvanometer, enabling us to measure larger currents accurately. These conversions are fundamental because they show how we can adapt a single instrument for different measurements by just adding the right components. It highlights the versatility of galvanometers and their importance in electrical measurement tools. Now, let's look at the key differences between ammeters and voltmeters. First, an ammeter is a low-resistance instrument, which means it is designed to allow current to pass through with minimal opposition. In contrast, a voltmeter has high resistance, so it doesn't significantly affect the circuit when measuring voltage. When we talk about their resistance, the ammeter's resistance is given by the formula Gs divided by G plus S, which is generally kept very low. The voltmeter's resistance, on the other hand, is the sum of G and R, making it quite high to prevent current from flowing through it when measuring voltage. Let's consider their resistances further. The shunt resistance in an ammeter is calculated as GIG divided by I minus IG, and this value is very small. This small resistance allows the ammeter to measure current accurately without significantly altering the circuit. Conversely, the series resistance in a voltmeter is V divided by IG minus G, which is very high, ensuring that it doesn't draw much current from the circuit. Next, regarding their connection in a circuit, ammeters are always connected in series because they need to measure the current flowing through a particular branch. Voltmeters, however, are connected in parallel across the component whose voltage we want to measure, to avoid affecting the circuit. Now, considering ideal instruments, an ideal ammeter has zero resistance, meaning it doesn't drop any voltage and doesn't affect the current flow. An ideal voltmeter has infinite resistance, so it doesn't draw any current from the circuit and measures voltage without influencing it. It's also important to note that an ammeter's resistance is always less than that of a galvanometer, which is a sensitive device used as a basis for these instruments. For voltmeters, their resistance is always greater than that of the voltmeter itself, of course, to ensure accurate voltage measurement. Finally, when we think about adjusting these instruments, increasing or decreasing their range, there's a difference. For an ammeter, It's not possible to decrease the range of a given instrument easily because it requires changing its internal shunt resistance. But for a voltmeter, it's feasible to decrease its range by modifying its series resistance, making it more versatile depending on the measurement needs. So, understanding these distinctions helps us select and use these instruments correctly in various electrical measurements and ensures accurate, reliable readings.